Okay. So, as we have already discussed about different kind of sampling, which is the major tool for doing pulse amplitude modulation. So, what will probably this will be our last class. So, what we will try to see is how this can be realized in a circuit first of all, and then from here how do we go towards a digitized version of this. Okay. So, that is probably the linkage of analog communication to digital communication. So, this is with this only will end our course. Okay. So, let us try to see what actually we employ as a circuit for pulse amplitude modulation. Let us say the natural sampling we want to do, because we have seen already some advantage of natural sampling. So, what we can do, let us take any switch. Okay. So, it can be a transistor switch or it can be a MOS switch, whichever switch you have this. So, basically what you try to do is you put your message signal MT over here. Of course, it is having bias. So, let us say VC. Okay. And you have a resistor over here, you also have a resistor over here. Okay. And over here what you do, you actually supply the pulse. So, this is where you will be supplying that pulse. Okay. So, whenever the pulse is high, that means it is on, at that time this will be on and there will be a current flow which will be proportional to the, because it is the message signal you are putting over here. So, that will be proportional to your message signal. So, if message signal varies in time like this, the current also will be varying according to this nature, and the voltage across this resistor. So, will also have similar variation, but whenever it is off, nothing will flow through it, because the transistor or that switch will be off and you do not get anything. So, basically what will happen at the output of this resistor, what you will see, whenever it is on, it will follow the signal, whenever it is off, nothing is getting flowed through it, again whenever it is on, it will follow the signal and nothing else. So, that is a natural sampling. We, with a very simple circuit, we can actually get natural sampling. So, that is also another advantage of natural sampling, that natural sampling can be realized with a very simple switch, either a CMOS switch or a transistor switch. It can be done very easily. Just supply the pulse, supply the message signal, and automatically it will be modulated with that switching. Okay. So, that is the realization of pulse amplitude modulation. Okay. What we can also do is pulse width and pulse position modulation, but probably for time savings we will skip those things, because those are not that much used and that is not that important. So, what we will try to do in this class is we will try to see from PAM how do you go to the digitized version of it. Okay. So, let us say I have either a natural sampling, but the natural sampling with a very small duration. Okay. So, that means it is almost equivalent to that flat top sampling, because the duration is so small that variation will not be it will be overlooked. So, it almost happens like a flat top sampling. Okay. So, if this is the pulse modulation that I get, now what I do is this particular pulse, I have got an amplitude at that particular instance. Okay. Let us say my message signal, it has a range, amplitude range. So, it varies from plus MP to minus MP. So, that is the overall range of amplitude variation. Immediately I can also say that pulse amplitude, because it is unit means the pulses are of unit amplitude. So, whenever we multiply, it just takes the message signals amplitude. So, basically even the pulse amplitude also will vary in that range. So, highest pulse amplitude can be plus MP and lowest pulse amplitude can be minus MP. Okay. So, this is the range over which it varies. So, I demark that range. So, from plus MP to minus MP. Now, what I want to do is I want to digitize this. Okay. So, digitize this means I want to have a unique representation of each of these samples, which can be represented by 2 bit like binary representation 1 and 0, which is easier to encode and easier to transmit. We will see the advantages of that also. Okay. So, I want to digitize it. What is the technique that I should employ? Whenever I digitize, let us say I digitize it with let us say 8 bit. Okay. So, that means each of the sample I will be representing with 8 number of bits. With 8 bit, how many representation I can get? That is something we know, 2 to the power 8 representation. Okay. That is 256 representation. So, if I do represent every sample with 8 bit, then I can only get 256 possible representation. But within this plus MP to minus MP, the signal is analog. So, how many representations are there? Infinite representation. Every voltage is a possible representation, but I only have restricted number of representation. So, what I do is a very important part where you go from analog communication to digital communication. So, you do employ a method which is called quantization. So, what does that means? Quantization means basically this range you take and you subdivide this range into multiple sub ranges. How many such things you will be taking? Exactly 256 such ranges, because you have 256 representation. So, you take small sub range, and any signal happens to be within this range will be encoded as the middle value, and it will have a corresponding binary representation or 8 bit representation. Why I have taken 256? Because I have with 8 bit 256 distinct representation. So, if this happens to be within this range, this entire range can be represented with a unique binary code, let us say all 1. So, 8 ones. Okay. Like this one can be represented with all 0 and so on. Every interval can have a unique representation, and what we do, whenever we represent it, that is all fine, that I get a signal which is in between somewhere, it can be anywhere. So, I represent that as the corresponding binary code. So, this is some kind of modulation again, means I am actually modifying the signal for a better representation, okay, so or a digital representation. So, this is some kind of modulation, and at the other end I have to also demodulate it, or I have to demap it, decode it. So, for decoding, what do I do? Now, I have this unique representation. Whenever I get this unique representation, I will be able to put a corresponding sample value over there, but now the problem starts, because which sample value I put, all these things from this, all those sample values in between, intermediate sample values, are mapped to this unique representation. So, when I demap, I have no information where exactly it was, because I do not have that information. So, what I will do, I will actually put the central point as the representation. So, immediately you can see there is an error, because it might be this one and I represent with the central value. So, basically the amplitude was this much, I have represented it with this. So, what might happen, suppose my message signals were like this, the samples are like this, and then I encoded with binary. So, anything falls under this. So, basically what happens, I represent it with the middle value, okay, and then I joins the middle values, whereas actually it should be this tips which should be joining. So, there will be little bit of error due to this quantization. This is called quantization error. Okay. So, whenever we digitize a signal, we will always be having a quantization error, and this process of digitization is called pulse coded modulation, because what you are doing is you are taking a taking a pulse and you are encoding it into a digital or mapping it into a digital bit stream. Okay. So, that is why it is called PCM or pulse coded modulation. Okay. Voice signal use this, means even these days also the telephony that you use, the landline phone calls you make, that goes through this. So, basically your voice signal, first of all it is being sampled with, because the voice signal we assume that it has maximum bandwidth as 4 kilohertz. So, what will be the corresponding Nyquist rate? That should be 8 kilo samples per second. Each of these samples are represented by 8 bit. So, overall bit rate will be 8 into 8. So, each of those samples are represented by 8 bits. So, 8 into 8, which is 64 kilobit per second. So, that is why the voice is always being transmitted with 64 kbps. This is a de facto industrial standard which has happened. That is because of this PCM encoded thing, which has 256 representation for quantization. Okay. So, whatever this is, we have now seen that there is a quantization error which is happening due to this process. So, can we characterize this quantization? So, let us try to see if we can do that. So, let us see my message, how it was. We had this interpolation relationship which tells me that this is actually nothing but samples taken at particular instance and represented by a corresponding sig function. Right. Whereas, my quantization one will be almost similar, but only thing is that instead of taking this, I will be taking that middle value. So, let us call that as m hat, because I cannot get all these values. This can be any arbitrary number, means any arbitrary value between minus MP to plus MP, but I will be taking some all those quantized middle point. Okay. So, that let us call that as m hat KTS, and that should be again, because these are creating a sample at the other end, I will be actually representing again with a sync function, so that I get my message back. Okay. So, due to this process there is a error. What is that error? So, let us say that is the quantization error, which is my this m hat t minus m t, which is nothing but, if I just represent it, k summation each of those sample error. So, m hat k t s minus m k t s into sync Okay. So, this is my quantization error. So, this is the error signal. I need to see how much power. So, this error signal is almost like a noise sitting over there, right. So, if I just try to see, this was my original signal, right, the above one, and this is my after quantization and demodulation or means decoding, this is what I get. So, the error is actually a noise as if being added on the signal to get my signal, right. So, that can be treated as noise. And how do we characterize noise? So, this is something which can be termed as quantization noise. Okay. So, this is a particular noise. If you see, whenever you go from analog communication to digital communication, this is a particular noise which is being created at the source. So far all the noise that we have talked about are either generated at the transmitter circuit, but which was very negligible. So, we have never considered that. In the channel, of course, there were noise, and in the receiver circuitry. So, mostly channel and receiver circuitry, that is where the noise were there. Now, this is the noise which is being created at the encoder. So, whenever you are quantizing, you are potentially creating noise. So, this is source induced noise. So, your process of transmission is generally creating this noise. Okay. So, this noise, how do I characterize a noise? We need to get the noise power. So, basically I want to evaluate the noise power. How do I get the noise power? So, I square it and take an average. So, in time domain, if I just write this, it should be this, the way we have defined power. Right. This is how we have defined power. So, this is how we should be evaluating that. So, if I now put the formula of Qt, so this was summation k q k t s. Okay. So, that m hat k t s minus m k t s, we are terming that as q k t s. Okay. So, if I just write this q k t s, this is sink square dt, right. Now, this is a homework you can take for your own benefit. So, what happens, we will be able to prove that this sink functions are mutually orthogonal for different values of k. What does that means? We will be able to show that from minus infinity to plus infinity, if we multiply sink 2 pi bt sum m pi multiplied with sink 2 pi bt minus sum n pi dt. So, that is two signals with different values of m and m. They will be orthogonal if m equal to n gives me some value and m not equal to n gives me 0. So, that is what happens. It is 0 when m not equal to n. This is something which you will be able to prove, and this is equal to 1 by 2b when m equal to n. Okay. So, these are orthogonal. So, what will happen? This square term, basically whenever you square it, there will be all square terms plus 2 into this cross term with different values of k like m and n. So, all those terms will be 0. So, only the square terms will be remaining. So, what we can write from here, it is nothing but t tends to infinity 1 by t minus t by 2 to plus t by 2. This will be just summation square term k t s, and this whenever m equal to n, that is the square term, that should be 1 by 2b. Okay. Of course, there should be this means that sink square will come, then you integrate, basically you get 1 by 2b, right. So, this is what we get. Of course, that dt goes out because you have already done that integration. So, with that integration you will be getting this because t tends to infinity is there. So, minus t by 2 to plus t by 2, that goes to infinity, and then that integration you can evaluate. So, you get 1 by 2b. I can write immediately limit t tends to infinity 1 by 2 b t, and then I can of course, this integration sorry, I have written in a little bit wrong fashion. So, I should have written this as sink square 2 pi b t minus n pi or k pi, okay, dt. So, I should have written this, and then the integration I can take inside because this has nothing to do this summation and this has nothing to do with that integration variable and limit. So, they can come out. So, I can always get 1 by, so this is equal to limit t tends to infinity 1 by t will be there, summation, this term goes out q square k t s, and then I will have this integration because t tends to infinity. So, this goes from minus infinity to plus infinity, this integration which happens to be 1 by 2b. Okay. So, this is how I can write this, and then what do I get? I get limit t tends to infinity 1 by 2 b t summation k q square k t s. What does this means? So, basically I am taking all those quantization value, the square of them. Let us say for a duration of t, how many such values I should be getting? I will be exactly getting 2b into t, because 2b is the sampling rate. Okay. So, per unit second I will be getting 2b such samples, in t duration I will be getting 2bt. So, what does this means actually? This means the average value of this quantization. So, q square kTs, it is the average value of that. Okay. So, whatever those values are, I at different k, I need to take the mean of this square or the average of that, because I am actually summing all of them divided by as many samples are there in t, and then t stretch to infinity means I take enough number of samples, so that it is actual average. So, basically I just have to do averaging of that, that should be my quantization noise. So, this is something we have proven now. Okay. So, now let us try to see how do I get this average. So, let us at this point I will be doing two things. One is we first assume, which is also a valid assumption, that this q thing, that is of course obvious, that will be a random process. So, basically what is happening, it is a discrete time random process. So, it has values at different time instance. So, this is the time description, but we also have an ensemble description of this one. Okay. So, there might be infinite number of such sample function which has different kind of variation, and we say that this is a stationary random process as well as ergodic. Okay. Without proof, but people have tested that that is true always. Okay. So, if that is the case, the ensemble average will be the time average. So, we were trying to calculate the time average, that must be the ensemble average, and now we will make further assumption that those samples, actual samples of m, means whenever we take m k t s, those samples are uniformly falling between minus mp to plus mp. So, they are uniformly distributed. So, a sample which are restricted over a particular duration, let us say that duration is del v, because the error will be only on that. It means he is always, any sample within this will be approximated by the central value. So, any error that can actually percolate, that will be restricted to the boundary of that particular zone. Okay. So, let us say that is del v. What is del v then? Del v is equal to, the overall range is from plus mp to minus mp. So, that is 2 mp divided by as many number of levels I will be creating. So, let us say that is L. For our case, our example, L was 256. So, 2 mp divided by L is my del v, and what happens? Within this, we are now assuming that the samples are uniformly distributed, that is what our assumption is. So, if the samples are uniformly distributed, what is the corresponding error? Because will be any sample we get will be representing by the middle value. Okay. So, the corresponding deviation will be from the middle value, whatever it is. So, let us say if it is uniformly distributed, the PDF should be 1 by del v, going from minus del v by 2 to plus del v by 2, because the middle point is the central point. So, what is happening? This is 0, this is minus del v by 2, and this is plus del v by 2. So, this is that whole range which is being represented by this. Okay. Within this, the sample might lie uniformly distributed. So, that is why 1 by del v is its PDF, and then I have to take q square. I want to take the average of that, whatever that value of q is, the deviation is the error. So, q square dq I will have to do, PDF I have already taken out. So, this if we evaluate, what do we get? It will be, if you just means integrate it and then put del v. So, you will be getting del v square divided by 12, that is the quantization error. Okay. Because I wanted to evaluate the mean of the square of it. So, that is what we are doing, mean of the square of it. So, mean of the square of it is square integrate over its range, which is the PDF range, which is from minus del v by 2 to plus del v by 2, and 1 by del v is its constant PDF. So, I get this. Now, what is del v? I can put that should be 2 mp by L whole square divided by 12. Okay. So, or mp square by 3 L square. Okay. This is the noise. This is called the quantization noise of a signal. Okay. So, now suppose I have transmitted a message signal mt, along with that I have a quantization noise which is qt, and I get this noise contaminated signal m hat, because we were actually receiving those m hat and we are connecting them only. So, we are getting this much error, this was the error signal. So, immediately what will be my S0, let us say that is the message signal's power. Okay. So, what will be my signal to noise ratio? That should be that message signal's power divided by the noise, which is mp square into 3 L square, right. So, this is how the signal to noise ratio is calculated in a typical this kind of PCM transmitter receiver. Okay. So, now let us try to characterize it little bit. So, what is exactly happening is something like this. You remember if we had, because it is a binary representation. So, if we have 8 bit, how many representation we were getting, or what was the L value? That was actually 256. So, if we have in general n bits for representation, we will be getting 2 to the power n equal to L, that many representation. Okay. All right. Or we can write that L is equal to 2 to the power n, or n is equal to log 2 this L. So, this relationship we know already. Okay. Now, let us also try to see what is happening to our overall bandwidth. Okay. So, we already know that every hertz I can transmit 2 bit. Okay. So, basically I had B, that is the overall bandwidth. I could eventually transmit 2 B samples, okay. And overall how much information I am getting. So, for this B bandwidth, because of Nyquist sampling, 2 B samples I am generating, because that is the sampling rate. Each of those samples are now represented by n bits. So, this many bits I am representing. Okay. So, to transmit this, how much bandwidth I require? This many bits per second. So, divided by 2 will be the amount of bandwidth I require. So, B into n hertz bandwidth I require. So, that becomes my effective transmission bandwidth, BT. Okay. So, basically I can write that my this value of n is nothing but my effective bandwidth, transmission bandwidth divided by B. So, this is the bandwidth I will have to take, okay, to transmit these things, because I have converted them into bits and then I am transmitting those bits. Okay. So, this is my effective bandwidth which will be occupying the channel, and this is the base means actual signals bandwidth. Okay. So, this is what I require. Now, if I now go back to the relationship between L and n. So, L is 2 to the power n, or I can write 2 to the power this BT divided by B, I can write this way. Okay. So, what happens to my signal to noise ratio? We have already represented signal to noise ratio as 3 L square m square T divided by MP square. This 3 and these things, if we just make them constant, suppose signal I put a particular fixed value of power MP, that variation remains same. So, basically this happens to be just some C L square. Now, L if we replace by this, we get C, L means 2 to the power n. So, 2 to the power 2 n, right, or I can write C 2 to the power 2 into Bt divided by B. Okay. So, this is something we get, that is the signal to noise ratio. Now, if I represent that signal to noise ratio in dB, so what I will have to do, I will have to take 10 log signal to noise ratio in dB. So, or we can write 10 log 10 C into 2 to the power n, that is what to the power 2n, sorry. Okay. Or I can write log, because it is log, so it will be distributed. So, log 10 C plus C is a constant, and log 10 2 into 2n, right. Now, log 10 2 is just 3. So, this happens to be log 10 2 into 10, that is 3. So, it is this particular part I can write as alpha log 10 C, because this is a constant, into 10, that is alpha, and here we can write 10 log 10 2, that is 3, 3 into 2 6 n. So, I get my signal to noise ratio in dB as this. Okay. N can be further written as alpha plus 6, n is, I have already seen that n is Bt divided by B, right. So, I have got a wonderful thing over here, probably you have not realized what has happened. You can see that as I increase my Bt, what does that means? I am actually taking more samples. So, suppose I go means increase my n from 8 to 9, immediately what will be the bandwidth increment? So, here the bandwidth is, if it is 8, it should be for voice channel, it should be 32 kbps or 32 hertz, the kilohertz. Okay. So, if you just calculate the way I have calculated, okay, 64 kbps, that should be, because every half hertz gives you 1 bit. So, 32 kilohertz. So, that is the bandwidth. If from there I go to 9, I get 36 kilohertz. So, only 4 kilohertz of increment of the bandwidth. But signal to noise ratio, what is happening, because n is going from 8 to 9, I get a 6 dB increment. So, a quadruple increment of my signal to noise ratio. So, basically here you can see, like FM, I increase my bandwidth, I get a better noise quality or better noise cancellation quality or signal to noise ratio. But the advantage is, in FM we have proven that if you double the bandwidth, then you get a 6 dB increment or quadruple your signal to noise ratio, whereas here you just increase by 4 kilohertz, that is not doubling the bandwidth, but you still get that kind of benefit. So, basically this particular thing has a huge potential towards the noise cancellation. You might be asking, okay, we have just taken the source noise, what is happening to the channel noise? So, of course, that is true, there will be channel noise also over here, but that is where the digital communication gets advantage. So, what happens in digital communication, whenever we are communicating a digital signal, so let us say I communicate like this, it is all 1 and 0, I know that it might be 1 or it might be 0. So, that is where digital communication comes into picture. So, suppose this signal goes through a channel which has a low pass characteristics, it has attenuation plus noise gets added. So, due to low pass characteristics, it will remain like this, and then on top of that there will be some noise added, and the signal will be look like this. So, all those nice pattern of 1 and 0 actually goes away. But the good part is, suppose you from here you start integrating it, what will happen? Because the noise is sitting on top of this and the noise mean is actually 0, because generally all the noises that we have seen so far, these are all 0 mean noise signal with some standard deviation. So, because you are integrating it, because what you need is just this bit, all like unlike analog communication, every location what is the value, that is not important. It is just we have to decide within this duration, is it 1 or 0, that is good enough for digital communication. So, what you do, you start integrating. So, these are the things which you will be learning in your digital communication, but I am just giving you some example so that you can understand. So, once we integrate, the noise effects gets cancelled, because noise will be 0 mean. So, if it is plus or minus, once you integrate, the noise effect will be cancelled, and because the signal, even though it is low pass filtered and attenuated, it will still integrate, and then you can put a threshold. If it is bigger than that threshold, you declare it to be 1, if it is less than that threshold, you declare it to be 0. So, that way you will have a very cleaner decision of 0 and 1, and what you can also do, you can actually regenerate in between. So, before the signal degrades to a limit or to a value where from you cannot really again reconstruct the signal. So, what you do in between, you put a regenerator which does these things, tell you that okay, this was 1, this was 0, reshape the pulse. So, again it reconstruct the pulses, because he knows once it is 0, then it should look like this, once it is 1, it should look like this, and again retransmit it. So, basically he makes the pulse again very nice and transmit it, so that you can combat the noise, attenuation and all other effects of channel. So, that is why digital communication is generally prone, it is much more effective in terms of noise cancellation and all other things. And we can, if we employ, and there are other techniques also to basically, if a bit is getting erroneous, you have other techniques to basically check whether it is erroneous or not, you can correct it and all those things. So, employing all those things, you can almost negate the noise in the channel or the receiver. Okay. So, then the quantization noise becomes the most significant one, and in quantization noise we have now shown that we have a huge benefit compared to all other modulation scheme, and that is the sole reason why pulse coded modulation started becoming very popular, okay, compared to its analog part. So, I think we have almost discussed enough of analog communication and almost came to the doorstep or doorway of digital communication. So, now onwards probably you can start discussing about how digital communication becomes effective and what are the techniques that are employed, how do you do noise analysis, what are the signal analysis that you employ in digital communication. So, those things can be explored further. So, with that I will probably end this course and from this onward you can take it forward towards more advanced communication techniques. Okay. Thank you.